Okay, so let's talk briefly about discrete convolution. So let me just write the formula we get when we are in non-discrete with non-discrete functions, functions from R to R. Okay, so f and g are from R to R, and we've got that f convolved with g is equal to g convolved with f. You know, you can exchange these. That's going to be the integral on R of x, f of x minus y, g of y dy, or the contrary. Okay, g of x minus y, g of y, f of y dy. Okay, so now let's consider discrete functions. What do we mean by that? Our function f and g are now going to take an input, a discrete input. So we can represent that as having an input in the set of integers, okay, z positive and negative integers, and they have a real value, so that for any p that belongs to z, you can get f of p or g of p, etc. Okay. What is that going to be used for? It's going to be used for digital applications, for instance, right? When you're looking at digitalizing a sound, that's going to give you a sample, right? So, for instance, your sound, if you're singing, whatever sound you emit, it's going to give you some sound wave. Okay, that's represents the intensity of the pressure of the air as the sound is going on through time. So that's time, that would be pressure, the intensity. And if you want to record it on a computer, you're going to, of course, you can't record. It's not an analogical process. You're going to record samples, right? You're going to record at some small and fixed interval of time, so you're going to record the value of your sound wave. Okay, so what you get in the end are those values, those discrete values. So you could call that f of at the first time step, f of the second time step, f of the third time step. Okay, so this is where we're going to digitalization. All right, you can still perform discrete convolution. What are we going to get? So let's write a discrete equivalent of this. F convolved with g, who is going to be a function, of course, that takes an integer input. Let's call that m. That's going to be equivalently to what was a sum, what was an integral in continuous functions. Well, in real functions, we're going to get a sum, right? So that's basically what the idea between discrete and continuous in the sense of continuous input. We get equivalent of integral is going to be sums. So sum, so now let's take p equal negative infinity to plus infinity of f of n minus p, g of p. Okay, and of course, you can exchange that. That's just going to be, you get the same idea that it's symmetric. So from plus infinity of f of p, g of n minus p. Okay, what's happening most of the time is that you will have your input signal called, well, the f is your input signal, and you will have your impulse response. Well, if I'm talking about sound, okay, let's take this analogy. So that's going to be the input signal, and you will want to modify this signal with respect to something that is called the impulse response. More on that in a bit. Impulse response. That's going to be something that has most of the time a finite support. Okay, we will take the example of reverberation of sound. Something of a finite support. That means that if G is our impulse response, G is non-zero on a bounded and finite interval, and let's call that from negative p to plus p. Okay, so that if you take a small p out of this interval, it's going to be 0. Right, so now if we write our sum, instead of an infinite sum, we're going to get a finite sum from negative p to plus p of, let's take the first expression, n minus p times g of p. Okay, well, it's just the same thing. It's just the bounds that are changing. Okay, so let's make a very simple illustration. So if your signal has first value f of 1, f of 2, f of 3, f of 4, f of 5, etc., f of n, and your g is going to have, let's say, 3 values, only g minus 1, g of 0, g of 1. Okay, so you convolve the two together. What does it give you? All right, so you're going to get f of g, f convert with g. Okay, let's take out not the first value because it's always a bit peculiar. But let's say if I want the second value of that, that's going to be, well, if you apply the formula, you're going to get g of 1 times f of 1, then you're going to get g of 0 times f of 2, then you're going to get g of minus 1 times f of 3. Okay, and all the other values of g being 0, that's just going to be 0. So that's g of 1, f of 1, you get g of 0, f of 2, and you get g of negative 1 times f of 3, and so on. So that will be the first one. If you're looking at the second one, at the third one, you're going to get this time g of 1, so I want f3, so g of 1 times f2 plus g of 0 times f3 plus g of minus 1 times f4, etc. Okay, right, so you see it's not very complicated. If you want to compute that with a computer, it's something that is fairly easy to create. All right, let's talk more precisely about the reverberation convolution. Okay, how it can be used in digital audio processing softwares, for instance. Have a quick look at some videos. You can find a lot of other things. Just type in convolution reverb on Google, and you'll get many more stuffs. Let's have a look at this.
Convolution is a mathematical process where two functions can be combined to produce a morphed version that has the characteristics of both. A convolution reverb is a signal processor that can be modeled to make an audio signal sound like it's in a specific acoustical space. For example, Carnegie Hall or the Taj Mahal. Typically, a very short duration sound is used to capture the characteristics of the room, like a balloon pop, an electrical spark, or more often, a starter pistol. The reverberation created by the room from the impulse signal is input into the convolution processor via a microphone, usually placed in the center of the room. The processor then strips out the original impulse signal, and what's left is the reverberation decay envelope. This can then be used to create the sound of that space. Another technique involves using a broadband sine wave sweep. This provides even more information, including the frequency response characteristics of the reverb. Sound designers will often use convolution to create very specific reverbs. For example, in the Lord of the Rings trilogy, Peter Jackson's sound crew used the convolution reverb characteristics of a garbage can to create the sound inside an orc helmet.
Thanks, Mr. Audio.
Okay, so thanks, Mr. Audio. Well, I guess you got the idea. You record the echo of a very short impulse sound, so that's it, and then it does something like that. You can extract the envelope with subtracting the original impulse, and then you convolve this with your signal. Okay, so that if you want to sound like you are singing in a big concert hall instead of your tiny student room, you can just record your singing in your student room and then convolve this sound wave with this response, and it will sound like you were singing in a very large room. Okay, so you get what this convolution is doing and how we can use that for digital signal processing in one dimension. Next thing is going to look at for images, and that's something that we can do during the tutorial. So let's have a look at this Wikipedia page, which is called kernel image processing. First of all, don't be afraid. The kernel here is different. Well, as far as my understanding goes, it has really nothing to do with the null space we talked about in the previous year. The kernel stands for something. Basically, it's a word that stands for something that is constant, that doesn't move, but whatever. Okay, so we're going to talk about convolution matrix. So we're going to do a convolution on an image. What is an image? An image is just a matrix of pixels, all right? So that at each, so you've got your pixels, so n times m pixels, for instance, for your image, and each of the pixel has an intensity value if it's black and white, or a color value for each three colors, red, green, and blue, and you've got the intensity of red, of green, and blue for each pixel, right? And in the end, that what you see is the color image that you have. All right, there are some very simple processes that can be done with convolutions. All right, so let's have a look at this. So first of all, you see the convolution formula for 2 dimensions, all right? So it's basically the same thing as before, except that you have 2 dimensions, and maybe we can have a quick look at how we could represent that. So you've got your array of pixels, so that's your image. Okay, so each square is going to be 1 pixel. Okay, it has location ij, all right, and you've got, let's say, n rows and m columns, and you're going to convolve that with some filter. Okay, and in the examples we saw, well, the first one you saw, for instance, is a 3 small matrix. Okay, that means that for any, so you are going to convolve that with this, all right, that's going to create a new array of pixels, a new image, right? Basically, you wanted to have the same number of columns and rows as the previous one. And how would you compute, for instance, that one? Okay, so let's say it's really the one corresponding to this one. Well, you're going to apply this, well, sorry, to this area of the original matrix, okay? But how do you apply this? Again, it's going to be, you have some kind of reversal process, meaning that this one here is going to be multiplied by this one here, plus, let's take some other color, this one here would be multiplied by this value here, and so on. Okay, so you're doing some kind of reversing, so that comes from the formula, and you just multiply, for instance, the green item from my filter with the first top left top pixel from the submatrix, and you sum all these, and that's giving you the resulting matrix here. Okay, so the resulting matrix in your entry. Right, so you do this for each pixel. Of course, you've got some specific treatment for the boundaries, but well, you can just loop them with the other side, but that's just one idea. But then you can fill in your new matrix, and with some very, very simple filters. So let's get back to the Wikipedia page. So identity, you don't change anything. The first one here. Edge detection, so you've got several small filters. So you see there are very simple matrices. You can do some kind of edge, well, you can do edge detection, you can do some sharpening and some blur, right? So let's say on some unsharpening and, well, combination of these things, right? So with convolution between your image and some simple filters like this, well, what is called a kernel, a convolution kernel, you can get some dramatic informations from your image, right? Like the age detections. So I think we should do that in tutorial. Take at least 1 hour to try this on images. All right. So that's it for today. Next, well, we still have, I guess, some time in the in the class time. So next thing is I propose you to watch an excellent video of 3 blue 1 brown again. That is going to introduce you to our next chapter, which is on Fourier series. Thank you very much. See you soon.